Okay, Assalamualaikum warahmatullahi taala wabarakatuh. We continue our lecture with topic 4. So topic 4 will include the design of ideal reactor for single reaction. So objektifnya adalah untuk you design different types of reactor. So again, different types of reactor are batch, continuous, PFR. So we'll be looking at on how to design these reactors. And when we talk about to design, is actually basically we're going to find what is the volume of mixture, what is the conversion, what is the concentration, what is the temperature, so this so on and so forth. So the design or to find all those values is actually based on what we have learned in previous online lecture yang mole balance, yang saya dah tunjuk on how to derive the mole balance for batch, continuous and also plug flow reactor. So untuk topik 4, I'm going to divide the video into 2 parts, and the first part is going to include on how to design ideal batch reactor, continuous stirred tank reactor. Other name for continuous stirred tank reactor is also mixed flow reactor. This is depends on which book lah. Ada buku dia guna mixed flow reactor, ada buku guna continuous stirred tank reactor. So but they are just the same. Kemudian in this video lecture also I will show you how to design the steady state plug flow reactor. So the next video for part 2 on topic 4, we'll be looking at space-time and space velocity, holding time and space-time for flow reactor, size comparison of single reactors. And also there'll be slides that I will just keep in, and I want you to read on your own, and it's especially those wordy or lengthy slides page kan, so you boleh baca sendiri. And also there are slides yang akan tunjuk contoh, so I want you to do that on your own as well. Before I continue further, I just want to step back the previous slide. So this slide is actually the summary of what you will be learned on topic 1, 2, 3, and 4. So if you look at this slide, the red law, the number 2 here, actually you have learned in topic 1 and 2. And then stoichiometry is what you have learned in topic 3. And mole balance is also what you have learned in topic 3. It's part of topic 3. The rest of it, which is the rest of the combine and all, is what we are going to proceed with topic 4. Okay, so after you've learned all these topics, I want you to look back at this slide, which it actually summarizes topic 1 until topic 4. Okay. Alright, so let's start with ideal batch reactor. So I want you to find on your own, apart from this information given in this slide on the application and also the advantages, I also want you to find on your own, especially other information of the application and also advantages of ideal batch reactor Um, in some of the references, books, YouTube's, Google, or other types of articles. But basically, the application of the batch reactor is especially for small scale production, and usually it's for pharmaceutical and biological type of production. The advantages of ideal batch reactor is easy to clean, usually will get higher conversion, and it's going to be some advantage on the for this reactor to produce uh, one product at a time, and then after this batch reactor is going to be cleaned and maintenance is done, then other product can be used in the same reactor, so it's gonna like reducing cost. Okay, in previous lecture I have shown you the mole balance and how to derive the mole balance of batch reactor. And this mole balance, if you change it into conversion, you will get this type. You will get this form. Okay, you will actually get this form of mole balance. So when you want the mole balance, is actually you need to be inserted into the rate law. So the rate law, there are chemical equations that will have the first order, or chemical equation that have second order. And you need to perform some kind of stoichiometry on that chemical equation. And so for example that we have the first order of that chemical equation. So you're gonna combine the mole balance into this rate law, and you eventually will get this form. So macam mana dapat is because of the stoichiometric here. So you masukkan CA ni kat dalam ni. So sama juga CA ni kalau kuasa 2 you masukkan kat dalam ni. So kalau you buat sendiri, you akan dapat this kind of form, this form. Okay, so bila you nak kira because when you combine, this is in the differential form, tapi bila you nak kira, contohnya you nak dapatkan nilai time, or you nak kira you nak dapatkan nilai x, so you have to integrate it in order to get the specific parameter. So yang ini I nak you buat sendiri macam mana daripada mole balance. So kalau you ada first order ni, and katalah kita ada stoichiometric begini, I nak you masukkan sendiri CA ni dalam first order ni, dapat tak equationnya begini. Sama juga ini, kalau you masukkan CA ni dalam equation yang ini, you dapat tak differential form untuk second order ni. So then bila you buat dalam integral form, you akan dapat bentuk begini pula. So I want you to do that on your own. Okay. So actually The next slide is actually dia ada tunjuk lah step by step sebenarnya. Okay, kalau previous video lecture saya ada tunjuk, ada introduce to you guys the mole balance for batch reactor is to have like this, is to be like this, okay? And then instead of number of moles and also volume, it actually can be changed, can be converted in terms of concentration. Sebab bila you bawa nilai V dekat oh sorry, okay, sebab bila we assume that it is well mixed, and if we differentiate it, this term, wait, let me recall something. Wait, suddenly I'm kind of blur of why is this term from NA over dt, and it comes to be the NA over V naught, unless wait. Okay, I want you to find the answer of how to change from the mole balance from number of moles, but it can change into concentration. It's actually in the book, in the Fogler book. But due to this situation, I kind of limited to get the book because the book is in the office. Okay, and alright, apart from that, selain daripada you boleh tukar kepada concentration, kalau dalam number of moles, but if you tukarkan dalam bentuk conversion pula, you akan dapat ni. Okay. Okay, so let's now have a look at the continuous stirred reactor or mixed flow reactor. So again, I want you to read on your own about the application and also the advantages. So kalau dekat slide ni, stated that the CSTR is especially for product that requires rigorous mixing or rigorous agitation, and it is where require continuous flow from in into out. Okay, jadi advantages dia adalah it's easier to clean, it has a good temperature control, and it also has low operating labor costs. Okay, in terms of the design equation, right, which I have previously introduced to you, that design equation for the CSTR you akan dapat dalam bentuk algebraic form ni. Okay. Daripada sini you tukarkan kepada dalam bentuk in terms of conversion. So macam mana dapat? Sebab kalau you ingat X pun sama juga dengan initial. So kalau dalam bentuk flow rate, so it's going flow in minus flow out. Oh, sorry. I'll start again. Sebab X is equals flow rate in my stylus pen minus flow out or remaining again divided by flow in kan. So kalau you tengok FA0 ni minus FA ni kan sama dengan ni. So dia masukkan saja. So dapatlah kalau in terms of conversion design equation dia begini. So kalau design equation dia you dapat macam ni, volume ni refers to the volume mixture of CSTR. So you dapat FA0 X over negative RA. So kalau kita ada data value of RA, negative RA and also FA0 X, kalau kita plotkan data FA0 over negative RA over X, bila you plot dapat graph macam ni. So volume of CSTR kita boleh kira this square. Okay. So itu untuk CSTR. Okay. Okay, kalau untuk PFR pula. Oh, ini adalah apa tu? CSTR kalau dia bersiri. Oh, okay. Dia bersiri pula, tapi bersiri but especially for single reaction kan. Alright. Kalau bersiri maksudnya the reactor is rearranged. You have first reactor of CSTR, kemudian dia tersusun secara bersiri second reactor of CSTR begini. So you have to perform the mole balance first at the first reactor. Okay, katalah first reactor ni dia ada ni FA0, kemudian dia ada volume 1, dia ada reaction RA1, kemudian yang keluar adalah FA1 dan telah berlaku conversion of X1 kat sini, dan FA1 ni masuk pula ke second reactor, and this second reactor has volume of V2 dan reaction of RA2 dan menghasilkan FA2 and also conversion 2. Okay. Hmm. Um, I just want to stress here, the X1 is actually conversion that happens in first reactor. But X2 here, okay, X2 ni is actually conversion happens for both reactor, meaning that X2 is the total conversion happens in these two reactors. So, jawab soalan saya, what is the conversion that happens at reactor 2? Berapa? So, jawapannya, conversion yang ada dekat X2 ni, dekat X dekat reactor 2 adalah X2 minus X1. Sebab tadi saya cakap X1 adalah conversion yang berlaku pada first reactor, but X2 is actually conversion that happens in both reactors, maksudnya total conversion. So kalau kita nak kira conversion yang berlaku pada reactor 2 adalah X2 minus X1. But go back to you need to perform the mole balance at reactor 1. So untuk CSTR, kalau you ingat lagi general mole balance yang kita belajar in topic 3, so dekat reactor 1, first that you need to put in, kemudian out, kemudian generation and then accumulation kan. So we assume that this CSTR is at steady state and it is well mixed. Jadi in, which is FA0, minus out, which is FA1, that is out from first reactor, and then the generation is RA1 V1 and accumulation is 0. Okay, so bila you rearrange and you tukarkan dalam bentuk conversion, you akan dapat this equation. Okay, kemudian you need to perform in the second reactor. So kalau in the second reactor, so second reactor in the materials that the materials that going into reactor 2 is FA1 kan. So yang keluar adalah FA2. Then the generation is actually RA2 times V2 and the accumulation is equals to 0. So bila you rearrange dengan conversion, you akan dapat this equation. Alright. Okay. So dia introduce the Dam-Kohler number. So the Dam-Kohler number is actually the ratio of rate reaction of A to the rate of transport of A at the entrance to the reactor. So ini dia punya formula lah. So don't really bother about it. You boleh rujuk buku juga. So the Dam-Kohler number, kalau untuk first order, you akan dapat tau K. Kalau untuk second order, you akan dapat tau K CA0. Okay. Okay. Next. Ini pula adalah continuous reactor, but if the arrangement is in parallel. So just now kita buat untuk series reactor, continuous third tank reactor in series. Tapi yang ini adalah continuous third tank reactor in parallel kan. Okay. So kalau untuk parallel, dia ada senang sikit. in which at every individual of reactor, dia punya cara you nak dapat is, this is the equation. Baik. Okay. So semua reaktor ni you akan dapat, the formula is going to use this general equation. So kalau first reactor, so just V1 FA naught X1 over RA1. So sebab semua reaktor ni dia adalah berdasarkan FA naught. Okay. So unlike apa tu, series reactor, you ada FA1, FA2. So ini semuanya FA naught. Okay. So dia ada cakap, since the reactor are of equal size, if the reactor are of equal size and is at the same temperature, so bermakna you have identical FE naught. And the conversion for each of reactor is also going to be the same. Yang ni. Okay. Alright. Alright, so ini adalah contoh on how to design CSTR. So again, as I said earlier, kalau maksud to design the reactor is actually you need to find what the concentration, what the volume mixture, what the conversion, etc. etc. So please go through this example on your own. Dan sebab dia akan ada its own solution. Okay, so you tengok step by step of this example and the solution. Okay, now saya akan tunjuk, saya akan introduce to you the steady state plug flow reactor. So basically PFR is actually being used in large scale of industries, and it's usually used for its having fast reaction and at high temperature, and it's going to use for homogeneous and also heterogeneous reaction. And its mode of operation is in continuous. So advantages of PFR is, of course, it's going to have a very high conversion per volume, and it's going to also have low operating costs and good heat transfer. So previously, in previous video lecture pun saya ada tunjuk the mole balance for PFR is going to be like this. So kalau you tukarkan dalam bentuk conversion, dan in differential form dia akan dapat begini, tapi kalau you integratekan dia akan dapat begini. So volumetric flow rate, kalau dia adalah steady state, so their volume per V naught is going to be the same as flow rate out divided by flow rate in. So kalau you rearrange, dapat beginilah. Okay. Jadi untuk kira volume of PFR, semestinya kena guna graphical method. And kalau kita ada data FA naught over negative RA, kemudian ada X, data of X, so you plot FA naught over negative RA versus X, and you akan dapat this kind of plotting. So volume dia adalah tu, the area under the curve. And how to calculate that volume is actually you need to use the numerical method such as Simpson's rule. So Simpson's rule ni you ada belajar masa first year hari tu dalam numerical method. Okay, ini adalah example kalau nak kira apa tu PFR lah, PFR punya apa on how to design the PFR. So dalam soalan ni dia memang tanya volume volume of production apa ni ethylene in plug flow reactor. So I want you to go through one by one sebab saya nak go through kan untuk awak dalam talian ni is a bit quite difficult. Dan cara paling senang juga adalah I want you to find or maybe I'll send to you some links on how to design ideal batch reactor, CSTR, and also PFR based on links yang or YouTube video yang telah dibuat oleh other lecturers in overseas. So with that, we'll continue in the second part of video. For this first part of video, I will send first to you, and I hope you get the objective of this, the first part of topic 4 of designing ideal reactors for single reaction. With that, I thank you.